So, in this video, we are going to discuss on the topic of frequency response of passive components. So, we all know that there are various passive components that we generally use in a circuit, which is nothing but the resistor, inductor, and capacitor. So, while we are discussing about the resistor, inductor, and capacitor, we all know that the frequency of the input which you are going to provide plays a major role in defining the how the circuit is going to work. Okay, so and also the source which you're going to provide, I can go with an AC source or I can go with a DC source. So the source which I'm going to provide also plays a vital role in defining how the circuit is going to behave. So, before getting into the actual topic of frequency response of the passive component, we should first know how the passive component, which is nothing but the resistor or inductor or capacitor, behaves for the AC or the DC source which I am going to provide. So, first starting with the passive component, which is nothing but the resistor, let us assume that I'm going to provide the DC source to the resistor. So in case of the DC source, we all know that the voltage and current is going to remain constant. So we can easily say that this resistor follows the Ohm's law, which is nothing but V that is equal to I into R. But if I provide an AC source to the resistor, we know that in case of the alternating source which I'm going to provide, the voltage and current direction changes continuously. During that time, I can define the voltage across the resistor as Vt that is equal to It into R, which is nothing but the reason for including the term T over there is nothing but the response of the circuit varies with respect to time. But when we are dealing with the AC or DC sources, in case of the resistor, it behaves almost similar in case of both AC and DC. But the variation majorly occurs in the capacitor and inductor. We all know that capacitor is nothing but a charge energy storing device, and it stores energy in the form of electric field. If I want to define this equation, I can define the charge storing equation as q that is equal to c into v, where v is nothing but the voltage and c is the value of the capacitor which I am going to use. So, if I'm going with a DC source, the current actually what is the workflow or what is the actual thing which is happening inside the capacitor is the current starts flowing through the capacitor will start charging, and the voltage across the capacitor will increase, and at a point the current starts decreasing gradually. I can also state this as after the capacitor is being fully charged, the value of current I will be equal to 0 and it behaves as an open circuit. But if I define it as an open circuit, I should know what is actually happening inside it, right? So the reason why I go with I is equal to 0 in case of fully charged condition is, again I'm going with the equation of the capacitor. So I'm going to define it as I that is equal to C into dV divided by dt, which is nothing but the derivative of voltage with respect to time. But since I'm dealing with DC current over here, we know that the voltage will remain constant, right? So in that case, if voltage is remaining constant, the differentiation value of dV divided by dt will be equal to 0, such that the value of I will be equal to 0. That is the reason we are defining the fully charged condition I that is equal to 0. But when we are dealing with the AC source over there, we know that there is a change in the voltage with respect to time, right? In that case, dV divided by dt will not be equal to 0. Therefore, I'll be having a value of I over there since dV divided by dt is not equal to 0. So the current will continuously flow, and the capacitor will offer an opposition force, which we call it as the capacitive reactance, which we can define it as Xc that is equal to 1 divided by 2 pi Fc, where the frequency plays a major role in providing the reactance to the circuit, which is nothing but an opposition force, which we'll discuss in later within this video. And next, dealing with the inductor, we all know that inductor will store energy in the form of magnetic field. If I want to define its equation, I can define it as V that is equal to L into di divided by dt. So if I'm dealing with the direct current, which is DC, I can say it as di divided by dt will be obviously equal to 0, so that the voltage value will be equal to 0, and in that case the inductor will be acting as a short circuit. But if I'm dealing with the AC source, di divided by dt value will obviously be not equal to 0, so that I can say the inductive reactance XL will be equal to 2 pi into FL.